Hi everyone and welcome to a new edition of Tech Talk. Today I am joined by two robotics labs at ETH Zurich, Margarita Klee.
Hi, thank you very much.
And we've got Dario Bellicoso.
Thank you very much.
Okay, and you guys are collaborating on a joint project. Tell me about what it is you're doing with search and rescue, I understand.
Yes, that's true. So this is a big Swiss-funded project about search and rescue. We're trying to build the robotic team of the future that's going to assist search crews navigate easier in the difficult circumstances of trying to find victims, maybe in semi-collapsed buildings or in avalanches. And what you are seeing here today is a collaboration between the Vision for Robotics Lab and the Robotics Systems Lab, both at ETH Zurich. In this collaboration, we have two robots, a flying and a walking robot, that they are each starting to build their own separate maps. And then as soon as these two maps experience overlap, so the two robots go in places where one or the other has been to before, then the two maps join in one. And why is this important? Well, that's important because that's the basis of any collaboration that will happen in the robotic team. But the idea is to enrich this team with more robots than just two. So we start with a robotic collaboration, and then once we have all the robots working in the same map, then we can have a mission assignment of where we want each robot to go.
All right, so let's start with that first robot in this collaboration, which I think falls in your camp, Dario.
Yeah, so one of the main focuses of the Robotics Systems Lab, which is led by Professor Marco Hutter, is this robot that you're going to see here. So it's all about building robots that we can send where we don't want people to be, either because it's dangerous or it's because of jobs that can cause severe stress. Imagine an offshore oil site where it's very dangerous to send people, or sewers, or bridge inspection where it's very dangerous kind of job. So we build robots that are supposed to go there, and then since these kind of places are meant to be operated by people with legs, such a system that we are building is very capable and flexible of navigating in these systems. Of course, this brings a lot of complexity, so there's lots of research and work going on, and that's why we're working so much on it. So I'm going to give you a short demo of what our robot is able to do and the kind of research that is ongoing.
I'm very excited because I've heard of, and I've seen quite a few images of this robot, and it's right here. Haha.
Yeah, so first thing, we have designed and built the whole system, both the robot and actually the actuation system. So the drives that are moving the robot have been completely designed and built by us. So this is a quadruped. It has 4 legs and 3 drives per leg. So the very, very specific characteristic of this robot is that a traditional robot is very stiff. It's supposed to just execute a certain motion, whether it's carrying a very light object or a very heavy one. On the other hand, when you're walking and when you're interacting with the environment and possibly with people, you want to be compliant. So what you see now, if I push the robot, this is a very compliant system. It will just, instead of being very stiff where it is, it's going to just respond with some compliance with respect to what I'm doing. So I'm able to do this. So this kind of actuation allows us to execute some motions on the terrain. It allows us to execute forces while walking, for example. And we can execute very different kinds of walking maneuvers, either very slow ones or faster ones where we can run and jump.
Okay. So well, he's walking away.
I better hold him. So I can actually hold him and pull him away. I can show you.
It's almost like you would do with your own pet, you know, when he's trying to get away from you, you grab him by the collar.
I can explain you what is happening here. So the robot is maintaining balance at all times. So this kind of walking gait is a dynamic one. It means that there are 2 legs in the air per time. So if you would just freeze the robot suddenly while 2 legs are in the air, the robot would just fall. So we build both the system and the software, so the brains of the robot, which allow him to keep balance. But this also means that if a disturbance is happening on the robot, imagine a non-flat terrain or a push. The robot has to be able to balance at all times. So if I push him in one direction, he's just going to re-step in order to maintain balance. With the latest research that has been going on, we can execute even more dynamic maneuvers. So we can do the same, but we can introduce some jumping maneuvers.
He jumps, so
So actually we can run. So imagine the same.
that is awesome.
So
It's more like a trot, isn't it? High five.
So what this allows you to do is, of course, it's not meant to be to jump in place. This is very useful if you want to run very fast.
How fast can he go?
So we recently did some experiments. We were running at 1.2 meters per second, which is pretty fast, and we can do much more. So this is the ongoing research that we're doing.
I want to have a bit of a closer look. So he is, I take it, now I've seen photos of him at the WEF in the snow.
Yeah.
So he is all-terrain, 4x4.
Yes, so he can go on any kind of terrain, exactly because we are modulating the contact forces. We can walk on such a terrain, or we can walk on ice, or even in water, because the robot is IP67, so it's waterproof. It's so the sensors that you see out around here. So this is a laser sensor, and this is an integrated sensor that we use for foothold planning. This allows the robot to have an idea of the environment around it, and allows it to localize itself.
To see somehow.
Exactly, so you can avoid obstacles, you can replan a certain motion. So you can command him to go forward, and if there's an obstacle, he will just try to avoid it. So this is meant to be used as an autonomous machine.
And he's battery operated.
Yes, so this is completely electrical. It has a battery inside. It has 3 pieces inside, each one dedicated to a different domain of the operation. One is dedicated to locomotion, so that's where the brain is essentially.
Where is that?
So it's all in here. It's all inside. So there's a stack of 3 PCs. One is dedicated to locomotion, one is dedicated to navigation, so for this path planning, and one is dedicated to applications, like if you would have a camera mounted or an arm mounted.
I mean, he's really fun. He's really fun, really spectacular.
So these are the
I was-
drives that we have designed.
And these are the cameras.
Yeah, so this is an integrated system. This has cameras. It has sensors which tell the robot what kind of motion he's experiencing. And this is what we're going to use to do the collaborative demo with the Vision for Robotics lab, such that the 2 robots can build a map together, combine it, and so imagine you have a swarm of robots that are all inspecting a very large field where you want to have information about it very quickly. So you can send a swarm of robots, they can build a map together, and they can collaboratively localize themselves.
How much does he cost?
I don't know if I'm allowed to say that. Enough.
Enough. You couldn't order him online or anything.
Well, you could if you have the money.
Well, you said there's a startup that is looking to commercialize it.
Yes, so this project has originally started here at the Robotics System Lab. Now there has been a spin-off out of it. So there's a startup, it's called ANYmal, and they are commercializing both the robot and the drives. So these drives have been used for this kind of robot, they have been used for arms, so they are very, very flexible.
And who is your customer for something like this? Who is this? Who are you thinking of when you make these robots?
So at the moment, I think that the robot is targeted for research labs. It has already been sold to some of the labs. There has been already some research output. But then I guess that the target is for whatever kind of operation you want to be autonomously done, where you don't want to send people because it's too dangerous for them.
All right, so the second part of this collaboration is Vision for Robotics, and that would be Margarita. Let's go have a chat with her and see what her lab is doing. All right, Margarita, now we are back to you. We've seen ANYmal in action, and now we've got Pegasus.
Yes, Pegasus, that's our flying drone. Now, in contrast to ANYmal, we don't really make these drones in-house. We are buying them. But what we do at the Vision for Robotics lab is to try and make sense out of the visual cues, out of what comes through the camera. So we are trying to build the robotic perception of robots. And in this case, we choose drones is one of our favorite robots to work with because they are fast and agile. They can navigate through doors. And actually, they pose some of the most difficult challenges for visual perception, which is what we're trying to work with. And so now you're going to see Pegasus trying to take off.
Now he gets quite loud, right?
Yes, exactly. So you can see it's a hexacopter. It doesn't really matter for what it is that we do. But so Pegasus has 6 rotors, and it has 2 cameras right now that you can see. We're only using 1 camera. It has an onboard brain, so that's a computer very similar to a laptop computer, and that's where we do most of our onboard processing. So really trying to make sense of what the drone is looking at every instant. And
How does it come together then with ANYmal?
yes, that's a very good point. So here now we're looking at a drone that's flying with a camera and a walking robot that's walking with a camera, its own camera as well. So every robot now is building their own map independently. So so Pegasus takes off, starts building its own map. ANYmal starts walking, starts building its own map. But at the moment that they experience some overlap in their maps, then these maps get joined with each other. So, and from the moment that they join, these 2 robots start essentially collaborating to continue to building and updating this map of their workspace. Now, why is this important? It's important because we might want to say, right, Pegasus, you can fly, you cannot really carry heavy computational power or heavy stuff, but you can fly further and tell us what ANYmal is about to see or where ANYmal can actually walk. So that's where then collaboration can pay off. Whereas ANYmal because it's a ground robot, it can port much heavier payloads in terms of computation, or even, let's say you want to transport some water to the victim. It's much better to transport it with a ground robot than a flying robot itself. So this is a project. So our collaboration is part of a much bigger project that is funded by the Swiss National Science Foundation. And it's a project with many principal investigators from this university here in ETH Zurich, from EPFL. So we have, basically, it's a Swiss-wide collaboration. It's much bigger than what you see here. And so here you get just a taste of what it is that we are trying to build. And this demo is really about developing the robotic perception, such that our robots are not just a set of cables and metal, but they can actually do something without someone all the time needing to pilot them.
So ANYmal is not the only robot that can use this kind of technology.
Yes, that's true. So now you see Pegasus and ANYmal running this visual understanding that we're trying to build. But essentially any type of robot that is carrying a camera and an onboard brain can really use this technology.
And where is this? Let's talk a minute about robotics in Switzerland. I mean, really key players in this landscape.
I would agree on that, yes. So we have very good researchers in different aspects of robotics, because robotics is really bringing disciplines, well, many different disciplines together. And we're also lucky enough to have very good funding from different sources. For example, in this project here, the funding comes from the Swiss National Science Foundation. So it's a very generous sum of money that Switzerland believes is going to help not only universities but also the society in general to start bringing robotics into helping humanity, helping society.
So in any case, the future is bright here for robotics in Switzerland.
I certainly think so and hope so, yes.
Well, thank you very much for your time, Margarita. I really appreciate it. We're going to call Dario over. Come over and say goodbye to us. Thank you again for your time and for introducing ANYmal.
Thank you very much for being here.
And we will see you guys next time.